of center. Mean and median are our main measures of center. We could use mode also. Now, you don't have to write down this, okay? So some of the things up here, you have to be a discerning note taker like you will be in college when you're sitting in your psychology class or whatever, okay? Some of the things up here are just to help me make the point visually so you can understand what I'm talking about. And then you'll want to write down like the main points or key things that's like, oh, yeah, if I was analyzing a data set, I'd want to do that. Let me write that down so I do that in my project, okay? This example, you don't have to write down. It's just cool for us to see the picture and understand a little bit about what it means to be skewed. Okay, so first of all, without even looking at the data, what are observations that you guys would make just looking at this chart? Okay? Just about shape or center or anything like that that you see when you look at something like this. Sean? Okay, good. So he sees that, like, in general, it started off really high, and then it gets lower and lower and lower, okay? For the type of data that's up here, does that make sense? This is salaries and percent of people earning that salary, okay, percent in our data. So does it make sense that a higher percentage of people would have this lower salary, okay, and it would kind of decrease as the salary gets higher? All right, what else do you notice about the data up here? This is just observations. Literally, you look at the data and state things that you notice. Is that it? There's a gap, okay? So it seems like the data ends, and then all of a sudden, there's this. So what do you think this is going to do to our data? Skew it, okay? It's got to affect our data somehow. Everything else seemed to be clustered right here, a nice little summary. And then all of a sudden there's this percentage of people, okay, that are beyond this $100,000 mark. So that's going to be significant in our data, okay? All right, so what they did is they took the data and they built the histogram, okay? You guys have built a histogram, so you've done something like this before, and notice that just by looking at the histogram, instead of the list of numbers, you could immediately see some different trends in the data and some different things that might affect your analysis, right? All right, so you guys said the word skewed, and so I want to talk about skewed data a little bit so that if you use that word in your data analysis, you use it appropriately, because it's kind of a little different than you guys would think. If you had to complete the sentence that says this data is skewed to the, what would you say? Okay. He would say right. How many of you agree with Nick? All right. Okay. How many of you are like, no, it's skewed to the left. All the stuff's on the left. Duh. That's what I would think if I just looked at it. Okay, I would think it's skewed to the left. He's actually correct, okay, because he has a little bit of a different background than some of us, but here's why. So here's something that would be important to write down, because in your data analysis, if you're going to make conclusions in your project about your data being skewed a certain direction, you want to be able to describe it properly. I'll pull down the screen. Sorry. So there's the information in words and then in pictures for those of you that are more visual people. So 3 ways to describe your data. Either the data is symmetric, okay, which means kind of like that bell curve, okay, and looks normal on both sides, or it's right skewed or left skewed. And visually, those actually look different than what you might think, depending on how you think about it, okay? Right skewed actually means that you have this bigger clump of data towards the left, and it's that little branch that's skewing out to the right. And you can see that left skewed means more of the data is over here on the right, and this little branch is skewing out to the left. Now, they didn't do that to confuse you. They did it because it's based on median and mean. So remember how did I tell you guys about the professor at University of North Carolina that talked about like average salaries of geography graduates? No? So he told his class, like, oh, it's great that you're here, okay? Here's why. The average salary of a geography graduate from this school last year, their beginning salary at their jobs, $250,000 or something like this. And this is in like 1980-something for a geography graduate. Any idea why that would be? Okay, maybe there was a small department and someone got bomb job, right? Okay. Somebody did get a great job, but does anybody know somebody famous that went to the University of North Carolina? Nobody? Back in the day, he played on the Chicago Bulls. Michael Jordan. So the problem is Michael Jordan just happened to be a geography major while he was at that school. So this professor was completely lying with statistics to his class because what he was doing was taking everybody else's salaries with Michael Jordan's in there and averaging them up and saying, this is the average salary. Well, I'm sorry, Michael Jordan's money, everybody else is making like $20,000 or something, right? And he is just completely skewing that information. So that's where we talk about like mean and median. In that case, would you really want to know the mean, the average? You don't really want to know that, okay? Because Michael Jordan is making that way wrong. But if somebody told you the median salary, would that probably be more accurate as to what people were making? Yeah, because even though his salary might be lined up in there, it's one salary at the end of the list. So the middle of the list is probably still going to give you a better idea of what the actual middle salary was, okay? So when mean and median are equal to each other, when you average it, and you generally get the same thing that you get when you line up all the data pieces and look in the middle, that's when you get this like perfectly symmetric data. Okay? The median is always in the middle because it's literally the middle piece of data. So that's not going to change. But does the average always have to be in the middle? Absolutely not. Okay? So what Michael Jordan would cause is this right skewed data. Okay? Because the median is going to be back here somewhere, and because of his salary, the mean is much higher than the median when they put that into the average. And so what it's causing is really most of the data is down here on the left side. But it's causing this little tail end, just like we saw in our histogram, to sneak off to the right because of a few pieces of data that are affecting that mean. Okay? And then you can see on the left skewed data, okay, it's skewed to the left because the mean is to the left of the median. So the way they describe the skew is about where the mean is in relation to the median. So again, the median is always in the center because it is the center piece of data. If the average and the center piece of data match up, then you have this like exactly symmetrical thing happening. If the average is more than what the middle piece of data is, meaning on a number line it would be to the right of the data, then the data is right skewed. Okay? If the average is less than what the middle piece of the data is, meaning it would be to the left of the middle piece of data, then the data is considered left skewed. So the name is really based on this information right here. So you can see that said in words right here or in pictures right there. So you should write down whatever is going to help you remember this best so that if you are doing single variable data for your project and you make a histogram or box and whisker plots or both, okay, and you're looking at the data and you're analyzing and you come up with numbers that are medians and means, you'll be able to compare them, and you'll be able to show us. So it would be pretty cool if you did it and you were able to make a histogram, and then you also had both these numbers, and you could show me, well, here's the median, okay, and I could see with your histogram the skew already, and then you can show me where the mean is to kind of confirm that this data is skewed a certain direction. Okay? So when people say skewed, the direction really depends on if the average is below or above, okay, to the left or to the right of the middle piece of data. Is this all right with everybody? Anybody still need the screen up to finish their notes? Okay. All right, sorry. Okay, so the second thing is that 5-number summary. So in addition to knowing what the middle is, you want to know more about this piece of data to understand a little bit better. Okay? So with height, we didn't just say like, oh, the median is this and the mean is this. We also went and found different quartiles. We looked at a box and whisker plot that specifically split up the quartiles so we could understand where the data was kind of compact and where the data was more spread out. So we already went through this. We just didn't necessarily call it the 5-number summary. So you have a minimum, then you have your lower quartile, or we called it Q1. Okay? Then your median, then your upper quartile, or Q3, and then your maximum. So remember when we had people stand up in front of the class, okay, and we saw that each of these areas has the same amount of data in it, but sometimes the data is really close together in that area. Sometimes it's really spread out, and that's what we like to look at. Okay? Like I was grading tests last night for my Algebra 2 trade class, and like I want to look at not only what the median ended up being, but were the scores around the median, like the 25% that's right above the median, was it really close to the median, or was it like super spread out? If it's super spread out, then I kind of wonder what's going on there. If it's really close to the median, that tells me like, wow, there's a bunch of scores, like half my class is right here gathered around like 80% was the median, right? Okay. So That helps me a little bit. I'll pause it and you guys can copy what you need. So the information at the top we completely discussed in class. So whether or not you're writing that information down totally depends on if you've been here and if you've been here. Okay? See what I'm saying? Physically and mentally. So when we did the quartile thing, we talked about minimum to first quartile is 25%. Therefore, the first quartile would be called the 25th percentile because it contains 25% of the data up until that point. That the median or quartile 2 would be the 50th percentile because it contains 50% of the data up to that point. Okay? It's like when you get the SAT scores back and stuff, I don't know, your CST scores, and they say, oh, you're in the 80th percentile. That means that you're generally at the mark that contains 80% of the data below it. Okay? So we did all of that. I liked the picture because I liked that it gave us a different way to see it. When we did our quartiles, how did we mainly look at the data? What kind of diagram? Boskin whisker plot for us to really understand, like 25%, 25%, 25%, right, in each part of a box or a whisker. Now, this is more like what it would look like. You can make a histogram, right? So technically the histogram wouldn't be curved, but remember we talked about why we like a histogram maybe over a bar chart, that putting the bars really close together just kind of helps us see the curve of the data. So once you could see that curve of the data, you can still mark on the axis where your quartiles are, and people can just see along your histogram, oh, this is also the median right here, so they can see half the data is above here and below here. So I like the idea that you can represent this data with box and whisker plot, or if it seems more meaningful, you can represent it with a histogram, and you can mark on that histogram where each quartile is so that people are still aware where 25% chunks of the data exist. Okay? Yes? Yes. So like the lower quartile, right? So we have our minimum point, right? So that's our minimum. So it's like the 0th percentile or something because there's nothing below it. So then that first quartile, we mark it because that's 25% of the data on one side of it and 75% of the data still above it. So when I am the 25th percentile mark, that means 25% of the data falls below where I'm at. Okay? And then the median, which is in the middle, is the 50th percentile because 50% of the data falls below. And then the third quartile is 75th because, does that make sense? All right, does anybody still need this page? So again, I just really liked it for the diagram because I wanted you guys to realize you can still mark those numbers on a histogram if you like the way a histogram looks better than a box and whisker plot because it's probably a more, I don't know, popular media representation of data than like a box. Like I never turn a magazine and see a box and whisker plot, but in a magazine I might see a histogram, right? So I put this on here to look at what we did look at. So we don't really need to draw the box and whisker plot. But the stuff at the bottom is important, okay? So if you decided that you were going to do single variable data, but you wanted to compare it in two categories. So let's say you wanted to do, this was what one of my Algebra 2 trig students did. They didn't go as in depth as we're going, okay? So they just made some general observations. But they compared GPA of APA students to GPA of athletes, okay? And there were some, they wanted to, they're APA students, and they felt like a certain stereotype exists, and they just wanted to see like if that was true or not. Now, they had to be really careful in selecting their data, because at first they're like, oh, we'll just pull this class, and I'm like, you're in an Algebra 2 trig classroom, okay? I was like, so first of all, I don't have like maybe as many of one student or the other in here, and two, like everyone's GPA in here is probably going to be like off the charts, crazy good or something, you know, okay, with a few exceptions. So they had to really go out of their way to sample other places and get that data, and then try to draw their conclusions from there, okay? So if you guys wanted to study something like that, because that's at least like an interesting topic, right? You would want to collect two sets of data, but you wouldn't be making a scatter plot with the data. It's not like height and shoe size where the two pieces of data go together. It's two completely different sets of data that you would then want to compare. So if you did do that, you would do these single variable calculations on the GPAs of APA students. You would then do the single variable calculations on the GPA of athletes, and you would somehow represent them. Side-by-side box plots. These ones are vertical instead of horizontal, no big deal. Okay, side-by-side histograms. But then how do you compare them? What would I want to know as a reader that would make me understand that you could draw a conclusion about one group being better than the other group GPA-wise or something like that. So here are the things you would want to do if you're going to compare single variable data but in two sets of numbers. Does everybody understand what I'm saying about that? So this means like you're collecting just one number but in like two different categories. Maybe you want to compare GPAs of girls versus boys, okay? And make a statement about gender and GPA in high school or something like that. You would do a bunch of calculations on the GPAs of girls, totally separate from your bunch of calculations on the GPA of boys, but then you would want to have a way to compare them. So if you choose to do something like this for your project, these are the things that would be important to compare. Centers, okay? Where is the median? Because that kind of tells me, do 50% of the girls, are they higher than where the 50% mark is for the boys? Are they lower? I want to know, okay? Amount of spread or variation. So like the lengths of the boxes or the whiskers in the box of whisker plots tell me maybe the girls is higher, but then it's like spread out all over the place where the boys might just be slightly lower, but they're like all right there, you know? Maybe that's better, okay? Shape, okay? Position of the median relative to the quartiles. Similar to spread, right? But not just size of boxes. Where is the median? Is all the stuff squished next to it on one side and then on the other side really spread out? That's important. Okay? And then the number of outliers. Okay? If there were outliers, you would want to report that. Now, here with GPA, unless there was someone who had like 0 GPA, I don't know if we'd have outliers. You okay? Sorry. Yes.
For number 2, there's those 2 dots above it. Are those 2 outliers?
Yes.
They just look a little abstract.
Yes. Okay, so in this graphical representation, yeah, Derek, if you guys want to go outside, you guys can go outside and talk, but the rest of these people have to complete a project that counts as their final grade and is like the last thing they're going to do. They need to know what they have to do. Okay. So, graphical representations. If you use box and whisker plots, Jordan was asking about these right here. She's like, they just look like marks on the graph. Those are 2 outliers. So remember, those were determined outliers how? How did you decide if something was an outlier? Okay. Good. So 2 ways. Either you could do the calculation if you like to have like an objective mathematical thing to fall back on. That was like 1.5 times the inner quartile range. Okay. Or 2, if you compared the distance between data points and one of them was ridiculously further away from all the other data, then you would consider that an outlier also. So my guess is whoever made this, they could probably pretty easily tell that that was an outlier, and maybe I might fall back to look at the math calculation on that one to decide how they determined if that one was an outlier. Because it'd be hard to tell with 2 of them, right? All right. Okay, so if you're going to compare 2 different types of data, but each are just about one number, okay, these are the different things you would want to mention in your data analysis portion of your project, okay? Because those different things are going to help us draw conclusions. Does anybody still need this slide? Okay, you're not going to write all this down either. Just the parts that you need. Okay, so measures of spread. The other thing you want to know, like I mentioned before, and like it said on the slide before, if you're looking at data, how spread out is the data? Your median might be like a really like good middle, like you're like, wow, that's really great. But if your data is then spread really wide and it's all in equal portions, like, okay, the middle was in a good spot, but there's still like 25% goes way out here and way out here. What does that mean? And it means different things depending on the kind of data you're looking at, right? Maybe spread could be good in some cases and maybe in other cases not. It just depends. We already talked about the IQR, okay, and that was the calculation that we were talking about, or it's part of the outlier calculation. Remember, the IQR is that area in the box plot where the box is. So it's from quartile 3 to quartile 1. You subtract those 2 numbers and you get a range between the quartiles, okay? So it basically gives me what are the maximums and minimums around that middle 50% of the data. The standard deviation is something we didn't talk about yet, and so that's what I wanted to talk about right now. All right, so standard deviation is a little bit hard to understand, okay? So I'm going to read you the definition, and then we're going to talk about what that means. So it says the average distance that the observations in the sample fall from the mean. Okay, what does that mean? Any ideas? or just a piece of it? So what's it measuring? What's the first word up there say? Distance, like an average distance. Okay? And then at the end, distance from what? From the mean. Okay, and what is the mean? What is the mean? The average, right? So let's say I took the height on campus of males and I averaged it and I got, I don't know, what do you guys think the average height is? We have some 14-year-olds. 5'10"? Okay, I think you guys are generous because you're seniors. Yeah. All right. That's okay. Let's just say 5'10". Let's say I took some data, I averaged some heights, and I got 5'10". Okay. Then let's say in comes walking, okay, my student that is 6'7". Okay. So let's say I determined that the average height was 5'10", and in comes walking my student that is 6'7". Okay. Would you guys say they are taller than average? Okay, that statement can be made very fairly because you know the average, they are above the average, they are taller than average. Okay. Would you guys call them very tall compared to the average or not that tall? Very tall. Okay, because I gave you kind of an extreme case, 6'7". But in the real world, you are not allowed to just say, oh, very tall, not so very tall, kind of tall. You're not. You got to have some comparison that we're comparing it to. So they set up a structure. Here's your mean, your average. I'm going to give you a measurement, and the further somebody is away from the average would mean the more extreme they are, right? On each side. If then somebody came walking into my room and they were 5 feet tall, would you say they were short compared to the average or very short compared to the average? Very short. Now, that's our opinion. How do we back that up with mathematics? So the way we back that up with mathematics is the standard deviation. So basically, the more standard deviations you are away from the mean, the further you are away from the mean is the more extreme value that you are. Okay? So if the average is 5'10", and then I have somebody that walks in that's 6 foot, maybe they're one standard deviation away from the mean, or maybe they're not even one standard deviation away from the mean. They're just kind of like clumped in there in the middle. But that 6'7" guy, he might be like 2 or 3 standard deviations away from the mean, right? So it's just like sections away from the mean, okay? So it's just a way for us to say how far you are away from the mean, if you're greater than it or less than it, okay? So basically it works out like this for those of you that want a visual. Here. And I'll come back to this page if you guys were copying this page. All right, so there are certain curves that are normal curves. Okay, the normal curves are the symmetric curves. Okay, what did a symmetric curve look like at that diagram we saw a couple slides ago? Like a bell curve, right? None of the skewing stuff going on. Height is probably one of those things that falls into that category. Okay? And in the bell curve, remember, the middle point is always your median, but when it's not skewed at all, your mean is also in the middle. Okay? So what a standard deviation does, let's say that these were our numbers. This was 5'10", we said we thought was this average height. Okay? Let's say that I said the standard deviation was, I don't know, 2 inches or something. Okay? That means that 2 inches above the mean at 6 feet, that would be 1 standard deviation away from the mean. Okay? Again, why do you care about this? It's only giving you a way to measure how far somebody is away from the mean in like standard little groups. Okay? The next standard deviation away from the mean would be like 6 foot 2 inches if we're going to do it every 2 inches. Megan?
So does there have to be like a certain amount of people at each height in order to make it standard deviation?
Well, what we're gonna see a calculation for it in a minute.
How do you decide after 5'10", 6 foot 2 inches?
Right, because I just made up that we had already calculated the standard deviation, and it was 2 inches. And so I went 2 inches this way, another 2 inches, another 2 inches. So basically, if I said somebody is 1 standard deviation away from the mean, then we're saying they're like 2 inches away from the mean, but not like 4 inches away, because then they would be 2 standard deviations away. So that guy that's 6'7", he's more than 3 standard deviations away from the mean in here. That then tells me, like, dude, he's a part of this little bit of the population out here. Like, he's pretty tall, right? But if someone came in and they were 5'8", I'd be like, they're 1 standard deviation less than the mean. Is that a big deal? And then we could make that decision later depending on what the data was.
Is there always a standard deviation for every graph then? So that you set and calculate it, or is that different?
There's not standard deviation for every graph you ever put in the calculator. There is standard deviation for any set of single piece data. So like a single variable data. So if you give me a list of data, I can find a standard deviation in that list of data. Whether it's valuable to me or not depends on how I want to analyze the data, but for any just like single variable list of data, I could find that. Okay? So does this at least make sense? So it's just trying to set up some standard measurement of how extreme somebody is from the mean, okay, or from the average. Like, are you average? Are you above average? Are you way above average? These little marks decide for you, and we call them standard deviations, okay? So like in IQ, if I'm like 10 standard deviations above the mean, I would just feel superior to everybody around me, right? Okay? But if I was like 1 standard deviation above the mean, like whatever, okay? That doesn't mean much. I'm not above the mean at all, I'm sure. I was just okay? All right, so are we okay with what standard deviation is? All right, then going back to the slide that we were on, because there's a couple things on here that you should pay attention to. Remember when we were just talking about the Michael Jordan thing and like, what would you report? Would you report the mean or the median of that data? The professor decided to report the mean of the data, because what was he trying to do? Yeah, it was the average. He was trying to make it sound better than it was. Now, he didn't technically lie. They call this like lying with statistics. One is to just like mess up the numbers. But he didn't mess up the numbers. He was very honest about the numbers. But he totally used a play on the numbers to meet his needs, right? And it was like way back in the day, too. All right, so there's 2 ways that we measure the center, mean or median. The mean is sensitive to that skewing. If there's a piece of data that's going to skew something, the mean is going to get extremely affected and probably not be a good representation of center, and then it would be good to go to the median. This is why I like to look at median with test scores, because I always have a student that like didn't do half the test, didn't pay attention, wasn't here, something like that. And like a 0 or a 20%, when it's the only one below 50% in my class, is going to definitely skew the scores in a way that I don't, I want a better measure of center. The measure of spread, okay, standard deviation measures the spread, but again, just like the mean could be affected by the skewing, so can the standard deviation, and then that's when the interquartile range comes in handy, okay? So if you look at your data and the mean and the median are really close together, you can probably use mean and standard deviation as good representations of your data. But if the mean is drastically different from the median because your data is totally skewed, then you probably want to use these more resistant measurements, the things that the outliers don't affect as much, okay? And that basically right here, it says what I just said. So if a sample has outliers or skewness, resistant measurements are preferred over sensitive ones. These would give us more accurate representation. However, if it's basically symmetric when you look at your data, then these could be good. How would you know? All you have to do is build a dot plot, histogram, something, a visual representation of your data, and you could probably see if it's skewed or not, right? Just like the pictures that we saw earlier. If it's skewed, then you're going to have to kind of resort to these measurements here. But if it's not skewed, you could mention these, but you could probably still use these ones over here. Okay? When she was like, how do you know it's 2 inches? Where are you getting this from? Like this kind of thing. There's a formula, okay? So there's a specific formula that calculates standard deviation. Okay? Write it down because we're going to use it in a minute to do a calculation ourselves, but eventually we'll have the calculator do it for us. But we want to understand what it's measuring. So first notation. So any x that they use is a piece of data from your data set. Okay? So there's like x1, x2, x3, x5, however many pieces of data you have, they're all in x. The x with the bar over it is the average that you calculated. And the n is how many things are in your sample. Okay? So if you look at the formula, I know it's like super weird, okay? But first, this part right here. The sample size, like how many pieces of data you have. Okay, so first of all, that thing I circled right there, that funny-looking E, that's the Greek letter sigma. Those of you that have been visiting some colleges, okay? That is the Greek letter sigma in mathematics. It means to add up. So basically, it's saying add up all the calculations you do that look like this, okay? What this is this is a piece of data minus the average and then squared, okay? So basically, you take your data. Let's say your data has 5. Let's say I had a really bad sample and I only polled 5 people for data, okay? I would add them up and divide by 5 to get the average, right? Once I had the average, I would take data piece number 1, subtract it from the average, square that number. Data piece number 2, subtract it from the average, square that number. Data piece number 3, subtract it from the average, square that number. I would do that with each piece of data. I would add it all together. I would divide it by 1 less than my sample size, and then I'd take the square root. Okay, the notation is what makes it look crazy. So what it's doing is it's trying to measure each piece of data, how far is it from the average, square it because we're trying to account for extra error, make that number a little bit bigger, okay? And then we're kind of averaging those things. We're adding them all up and dividing by something. The reason they're dividing by 1 less is, again, to account for some error, okay? We'll do this, but in the end, we'll do it all in our calculator, okay? Does anybody still need the formula? Okay. So what we're going to do is we're going to get a mean, and then we'll see how far we get, and then we'll just finish tomorrow, whatever we don't finish. So here are 2 brands of paint. So a testing lab wishes to test 2 experimental brands of outdoor paint to see how long each will last before it fades. So they make 6 gallons of each paint to test. The 2 groups consist of very small populations. So we have to take that into consideration with our data. So like when you do your project, the first thing Nick asked me was like, how much data do we have to collect? And that is a valid question because in order for it to be good data, more is better, right? So first we just want to find the mean of each group. So you can take out your phone calculator or whatever and just find the mean of each group. Look at our data in all aspects. So first thing we calculate the mean, we get 35 for both of them. So if this was my data experiment, first of all, it'd be flawed because I only have 6 samples of each. But if I was looking at this and I was trying to take each data and then compare them, so the first thing I do is calculate this mean and say, well, the mean for them looks the same. So if I use that as the measure of center, it seems the same. But I also want some visual to understand the data. So here's a visual. And this is where your observations become important. Remember I said it's not just about the calculations with statistics. You have to be able to look at some data and observe some things as well. So both of these had a mean of 35. The average was 35. But looking at the visual, if you had to choose a can of paint to go paint outside somewhere at your house, which one would you choose even though the average time it lasts in months was 35 for both brands? Would you choose brand A or would you choose brand B? Brand B? Brand A? Okay, why? The people that said brand B, why? Shortage.
Because, I mean, for brand A, you might have 6 months, you might have 10, but for brand B, you know it's going to be somewhere around 35 months because that's where other people have put for it.
Okay, good. So what Jordan is telling me in a more mathematical sense is that the measure of center here, 35, for brand A, is the center, but it's totally a gamble, right? You might get something that lasts up to 60 months, awesome, or you might get something that lasts 10 months because it's so spread out. So this is where the spread comes important, right? It's so spread out that 35 just happens to be in the center, but isn't maybe really representative of the paint. But she's saying here in brand B, if you're really looking for something that kind of meets that average requirement, at least here the data is more grouped around 35. It peaks at 35, okay, and it's not that spread out. It's right in here that 35 might be more representative of the data, okay? All right, so the next thing that we're going to do is we're going to calculate the standard deviation, okay? So here's what we would do if we were doing the standard deviation by hand. Tried to pick something with not a lot of pieces of data, and now you know why I after seeing how we have to calculate the standard deviation. So it's important that we know the mean. So first of all, the mean is 35, okay? So remember what the standard deviation calculation said to do, okay? We have to do a bunch of stuff, right? How many pieces of data do we have? 6. That means 6 times we have to take the data number minus the average, square it. Okay? We have to do that with all 6 pieces of data. It's going to look ugly for a minute. 60 minus 35 squared. I'm using brand A. 50 minus 35 squared. 30. Am I almost done? No. 40. And 20. Okay. So there's all the little different squares that I have to calculate, and then once I do this, I have to add them all up. Okay. After I take all those, subtract them, square them, and add them all together, I want to take that, and I want to divide it by 5. Okay, because where is she getting 5? 6 minus 1. 1 less than the data set. So I do all this stuff, and then at the end, I take the square root. Okay? So let's take a second and do that calculation.